Good morning all. So today we are going to discuss the parallel single phase AC circuits. We have the different configuration here, RL series, RL parallel RL circuit and parallel RC circuit and parallel RLC circuit. We will see the behavior of all these three kind of the circuits. So let us consider the first one. Let us consider the first one is the parallel RL circuit. Parallel RL circuit here. So as you know, what is this my parallel is, your inductor is connected in parallel with your resistor. So this is the going to give a parallel combination of this L and C. This is R, this is L, I can say. This is nothing but this is, I can write Vm sin omega t, and this is the I is the current drawn by the source, and this is the current in resistance, and IL is the current, and current is flowing in your inductor. So I can write here that is V is nothing but the instantaneous voltage Vm sin omega t, and where I also I can write this is nothing but IR plus IL, I can write. So what is I here? That is nothing but V by R is equal to V by, sorry, this is V by Z, right? Because it is the impedance, I can write. So this is V by Z, and what is IR is nothing but V by R plus, how will you write IL? IL is nothing but 1 by L, the integration of V dt. So this is the expression, you know how to write this one. So after this, what I'm trying to do here is, so what is the V here? V is nothing but I can write Vm sin omega t by R plus 1 by L, the integration of Vm sin omega t. I can take, this is nothing but I can write here. So I will write first here. So Vm sin omega t dt, and if you do this one, then what you are going to get here is Vm sin omega t by R minus Vm by WL cos omega t. So this is nothing but V by Z. So you are, what you are getting here, Vm by R sin omega t plus Vm by W, that's omega L, sorry, not W, it is omega L sin omega t minus 90 degrees, isn't it? I am converting cos omega t into 90 degrees. So if you see here, this is nothing but your IR current, and this is nothing but your inductance current. So IR current and inductor current, if you see the difference, so this is the 90 degrees is lagging by your IL current. That is what the information you are getting, isn't it? So if you take, this is my voltage as a reference here. So this is my voltage as a reference. Then what about my IR current? IR current is in phase with this voltage. In phase with this voltage. This is my IR current. What about my IL current? IL current here is, IL current is 90 degrees is lagging. So here somewhere is my 90 degrees is there. So my it is my IL current is lagging by IR with some 90 degrees. So this is, I can take, this is my IL. So this is how you can represent your different diagram. If you talk about the vector phasor vector representation, then this is my V reference. Along with this is nothing but my IR is there, and this is 90 degrees with respect to this one. I can take, this is the IL is there, and the component of these two, if you write, then this is nothing but your I, isn't it? So this is nothing but your I. So this is what the pi angle, you can say this is the I. So I can say this is I vector is equal to IR vector plus IL vector. So something that you can show the diagram here. So this is what we are trying to getting the for this kind of analysis you can do for RL's parallel circuit. Now go for the second one, is called a parallel RC circuit. Parallel RC circuit. Now go for the parallel RC circuit. Again, if you take the diagram, this could be the diagram you are getting for your this RC circuit. Then I can write, this is the C and this is R, and this is the current I is flowing, so V, and this is the IC current, and this is my IR current is flowing again. So my I is equal to, I can write, this is IR plus IC, and Ri is equal to, this is nothing but V by R plus C dV by dt. Also I can write, convert into current waveform here. So how will you write this one? This is nothing but Vm sin omega t by R plus C d by dt of Vm sin omega t. If it is there like this, then I can write this one Vm by R sin omega t plus this one I can write Vm by 1 by omega c, and I can write this is sine into omega t plus 90 degrees. So I am converting into that kind of formula here. So this is look like this is IR plus this is IC. Again, if you draw this one, same, what you are going to get here, my IC current is leading here, isn't it? So this is my V, I can say, and suppose this is my in phase with my voltage going, this is my IR, then my IC current is leading by 90 degrees. So it can be come from here. So like this, I can show my IC current here. So this is what, and if you see the phasor diagram for this, so then V as a reference if you take, then this is my IR, I can say it is my IR, and this is nothing but my IC, and this is nothing but my I. So this is what we are trying to getting the pi angle. So this is the one of the analysis also you can do for your parallel RC circuit. Now what is the third one is? Third one is we are going to see the parallel RLC circuit. Parallel RLC circuit. So here also you can do the similar analysis what we have done for the two networks. Similar analysis also you can do for this one also. So this is my series RLC circuit, and this is my current IL and IR and IC, you can say. Then my current I is equal to, I can write this is IR plus IL plus IC, or you can write into Vm by R sin omega t plus this is, I can write integration of this one if you take, then directly you can write this is a minus 1 by omega cos omega t is coming here, it is plus omega cvm cos omega t is coming. So or you can write into simplify this one, then Vm by R. So I am writing the direct steps I am writing here, so you can go for the simplification in detail of later of this class also. You can try, you will get the same equation what I am showing in this explanation here. So this is my current. So like that also you can show the different concept here, and you can go for the any kind of things also you can be analyzed here. So I have to talk a small concept here, that is called solving the parallel circuits by using admittance and Phasor algebra. So this is the concept I will discuss now. How to solve the parallel circuits by using admittance concept and Phasor algebra. So what is this admittance concept is? So as we know that our loads are a combination of inductive and capacitive load. Inductive means RL combination, capacitive means RC combination, or sometimes RLC combination also there. So if I see my net loads here, different load, then this is my load I am showing here, but inside of this load what kind of load it is I am not showing. It may be RL, it may be RC, it may be RLC, something like that may be have the load, and this is what the generalized circuit I am trying to show here. So this is my current I, and this is the impedance, I can say Z1, this has the impedance Z2, and this load has impedance Z3. So current drawn by this impedance load is I1, current drawn by this one is I2 and this is by I3. So what is the total current I can write here is I is nothing but I1 plus I2 plus I3 I can write. What is this I? Nothing but V by total Z. It is nothing but V by Z1. It is nothing but V by Z2 or it is nothing but V by Z3 I am writing. Or I can convert the Z into this Z into a admittance. So I can write, so convert this one. So this is nothing but V into Y is equal to V into Y1 plus V into Y2 plus V into this Y3. So this is also we are getting the kind of expression. So this kind of expression is needed to solve the parallel circuit. So that is what the concept I wanted to discuss here. So we'll take one network and we'll do that one. So let us again consider a parallel RL circuit. Let us once again consider the parallel RL circuit of this V. You can say this is the I is there. This is the voltage phasor voltage, and I can take this is the I1 and this is I can take I2 and this is my R, and I can say the reactance of this inductor is XL. And I know this I is equal to, I can write I1 plus I2 or V by Z is equal to V by R plus V by JXL. So instead of I2 I can write V by that reactance I am writing. So V by JXL. So you also know this one, how to write this one is, so what I am trying to do is I will multiply with J here and here. Then what happens is that one I can write V by R plus J into V by, instead of J square I will get minus 1. So I can write here minus 1 and I can remove this one. I will get minus XL. So this is what I am writing here. V by R minus JV by XL. This is nothing but V by Z. Otherwise you can go V into Y is equal to V by 1 by R minus J by XL also. Otherwise you can write this into G. You can say it is a G V into G minus JB. So this is also one kind of the expression. So these are the different configuration you can understand, so that if any numerical will come you can easily solve those numericals. So this is the phasor diagram in the conductance and susceptance. So this is nothing but my IR, or you can say it is the VG, and this is my VB, isn't it? And this is nothing but my VY. So this is what the pi. So this is the phasor diagram or triangular waveform for this one. Now similarly do the analysis for single phase parallel RC circuit. Do the same analysis. Let us consider, so this is my single phase RC circuit I have, and for this circuit this is my V and this is my I, R and C. You can say this is IR, you can take this is IC. Okay, then how will you write the concept here? So if you take V is reference here, V as my reference, then this is nothing but my IR and this is my IC and this is my I. How I am writing, you know, so how to write this phasor diagram for this one. So where my I is lead voltage by some angle pi, so that's why it is RC circuit. Now apply the KCL here, apply the KCL and write what is the I is equal to, I can write IR plus IC. So all these are the phasor forms I am writing. So here it is nothing but V by R plus I can write here this one is nothing but V by JXL. So finally this expression we are going to get V by XC. So this is what we are trying to getting from this one. or I can write this one here again once again. So this is also I can write as, so I can write I by V is equal to 1 by R plus some J by XC also I can write. So this is I can convert this I by Y is nothing but Y. So it is nothing but simply 1 by R plus J into 1 by XC. So these are the different representation of your equations. You can get 1 by XC by 1 by R also. So pi R, you can say pi is equal to tan inverse of R by XC. So these are the different representation you can use to solve the networks. Now the next one is the single phase parallel RLC circuit. RLC circuit. Then what is the analysis? How we are going to do the analysis here? So let us consider I have a network like this. I have a R is there. I have, so C, L and R is there, and I'm supplying a single phase AC system to this network. Single phase AC system V, and this is the current I. Again I am taking, this is IR, this is IL, and this is my IC I'm taking, and I will assume this one is then this is my reference angle. I can take V reference. How to see V reference? Then this is my IR, but this is my actually the IC, and this is my actually the IL, and my condition is, suppose my IL is greater than IC, then what could be the scenario here? So there may be, here it will come IL is greater than IC, so IL minus IC is the value is coming. So if we do this too, then this is what the my net current I you are going to get. So I, isn't it? This is how you are try to getting the phasor for IL is greater than IC. If you take that IC is greater than IL, then the equation is different. If it is IL, then IC. Now if my IC is greater than IL, then IC minus IL will come, and this is what my IR, then this is the resultant I you are going to get. This is the pi. So where it is my IC is greater than IR. So here this is the voltage as the reference. So this is how we have already done this kind of analysis for a series RLC circuit. Similar analysis, but little different here. So you can go through this equation. You can come to know how we are drawing this equation and the phasor diagrams. Now we'll go for what is the IR here. It is V by R. If you want to write what is IL, IL is nothing but V by Z into XL, or I can write minus J into V by XL. This is also I can write. What is IC here? V by minus JXC, or I can write J into V by XC. I can write like this. So if you take what is I, total I is nothing but IR plus IL plus IC. These are the phasor forms you try to write here. So I can write what is this, V by R minus JV by XL plus JV by XC. So this is the concept. If you take this one, then you get 1 by R plus J into 1 by XC minus 1 by XL I can write, and this is I. So I by Y you can take, then simply you are getting 1 by R plus J into 1 by XC minus 1 by XL. So this is what you are getting, and this is I by V. I by V is nothing but Y, admittance is nothing but 1 by R plus J into 1 by XC minus 1 by XL. So these are the different ways you can represent. What is the magnitude of Y is nothing but under root of 1 by R square plus 1 by XC minus 1 by XL whole square. So this is what we want to find. What is the phase angle tan inverse of this one, 1 by xc minus 1 by xl by 1 by r. So this is what the tan inverse will going to get. So these are the different analysis you can able to do to solve any network. Now we'll take some numericals, one or two, so that this kind of analysis can be more clear to you. So let us consider I have a R, L is there, and which are connected in parallel. We given the supply here 230 volt supply with 50 hertz is given, and this is the 10 ohm is there, and 0.05 henries is given. I want to find what is the total current IT, what is the impedance, what is the admittance, what is the power factor, and what is the apparent power, what is my active power, and what is my reactive power. All these kind of things I will going to answer in this network here. So if you see this one, if you want to find what is IR, this is nothing but V by R. So 230 by this 10 volts, if you take, then 23 by 0 angle, this is the amperes we are getting. If you want to find what is the IL, is nothing but again 230 volt, that is you can talk here, it is 0 angle is this one by XL. So XL I can write this is nothing but I have to convert the henries into XL. So L is there, so I have to convert into 2 pi f L, so that is going to give me XL. So I can write this is the XL value. So 230 into 0 degrees by J into what is XL here. XL you are going to get some value, that is the you can write it is a 2 pi f into 0.05 henries. So final value you are going to get is nothing but 14.65 with the angle of minus 90 degrees. So because this is J operator, so this is you are going to get 90 degrees, then you can do this one, then you are getting this value. So that is what. Then what is the I total? I total is nothing but this IR plus IL. So you will getting this one, if you do this one, 27.27 and minus 32.50 you are going to get from this concept here, 23 and J14 of minus IL. Now if you want to find what is the impedance here, impedance Z is equal to, that is the total voltage by total current, then 230 is angle of 0 by 23 into J 14.65 is the total current. If you do, you convert this into a polar form, and this is already in polar form. If you solve this one, then you will get, this is the answer. If you have, you can try this one, you will get this one. And what is the admittance? This is 1 by Z admittance. So this is nothing but 0.10 minus 0.06 J. You can do this one, then you will get this one. What is the cos pi here? The cos pi is nothing but I can write it is the tan inverse of R by XL, isn't it? So I need the pi here. So if you do this one, you will get 32.5 degrees. Then power factor is nothing but cos of 32.5 degrees. So you will get 0.54 lagging, because this is the RL load. Then S is equal to, I can take this simply VI and 230 into 27.27. Then if you do this one, 6272 volt ampere you will get. And what is P is nothing but VI cos pi. You do this one, you are going to get 5.268 kilowatt. Reactive power VI sin pi. Do this one, you are going to get 3.386 kVAR. So this is the way you can solve this kind of networks. So with this formula, so I hope you understood this concept, and I will stop for today's session.